Good afternoon. So welcome to the natural language processing class. In this class, we will learn the basics of natural language processing technology, including how you build models, how you derive the theory behind. And you will also have a chance to practice, build a natural language processing project on your own. Okay, so for this week, we're going to make an introduction. So you'll take a brief overview of what natural language processing is about and a brief overview of my course, right? So that you will have a chance to quit it or to select it, okay? I'm going to discuss three major topics. So the first is roughly, what is natural language processing? Okay. The second is, I will show you what kind of tasks this field has been solving and is trying to solve right now. Lastly, I will tell you why you need to learn natural language processing from a machine learning perspective, why machine learning is very important, and how we organize this course. Okay, so first of all, what is natural language processing? So in the broadest sense, right, natural language processing refers to any algorithms that deal with languages. Okay, so a very simple case is a string matching algorithm. For example, a regular expression. I think for you who have learned Python, C, right? You know how to compile a small regular expression that matches how many numbers, how many times the letter A appears in a string, right? Or to match whether a string contains, for example, teaching, etc. And in the other end of the spectrum, natural language processing also covers what I think everyone uses right now, right? Large language models. You use ChatGPT and you use DeepSeek to answer your daily questions, help you organize some writing materials, etc. Okay, of course, not with your homework. Surprisingly, these latest large language models are very smart in the sense that they can answer all the homeworks behind my textbook correctly, right? They're very intelligent, which I will mention later towards the end of this term, okay? But now, what is natural language processing? Let's take an overview of the field, okay? What have people been doing in natural language processing? And if you look at the whole field, you'll realize the tasks people solve are in a very broad range. People solve a broad variety of tasks, but I can roughly categorize them into four main types, right? The first is called computational linguistics, okay, or fundamental NLP. The second is called information extraction. The third is called natural language generation. And the fourth is miscellaneous, sort of other related tasks. So we will look at them one by one. So the first one is called computational linguistics tasks. Okay, so this is a very traditional branch of natural language processing. Okay, which are less and less interesting to the students in research, but they are quite fundamental. Okay, so computational linguistics is a field in between AI or computer science and linguistics. So linguists, they study the phenomena or the regularities behind languages. Okay, and computational linguistics study how do you use algorithms to help linguists solve this phenomena. So when we look at linguistic studies, we can look at there are a lot of different categories of things people are interested in, right? Phonology, so how things pronounce, phonology. Morphology, how to spell things, right? Syntax, right? How to say something that is grammatical. Right? Semantics, how to represent the meaning, all right? Also discourse, how do you organize different topics into a coherent paragraph, right? And pragmatics, right? The intention of your words, okay? All these things. And almost everything has been studied by computational linguists, okay? So I will walk you through all of these, okay, to take a brief overview. All right, first of all, okay, let's not to mention phonology, which studies the pronunciation, how to turn text into their pronunciation, expressions, or vice versa, okay? But on the word level, right, people study morphology and segmentation. So what is morphology? So the words, for example, the English words we see every day, okay, can consist of a lemma and some morphemes that are composed. For example, if you look at the word walking, right? So it's a gerund. Its lemma is walk. And there's an ing suffix to it to express something that is happening, right? Okay, so morphological analysis uses algorithms to automatically segment these words into their morphemes, okay? So to analyze the spelling. So different languages have different levels of morphology. If you look at languages such as Chinese, Japanese, and Thai, these languages do not have much morphology. But if you look at languages such as German, maybe Czech, etc., these languages have rich morphology. So in these examples, I showed you an Arabic example, a German example, where a very long word composed of a lot of morphemes express complicated meanings, okay, as you can see in these examples. Now, for Chinese, you don't have morphology, but the sentence is written as a sequence of characters, right? So in order to understand the meaning, a token level task is called word segmentation, which is to chunk the sequence of characters into a sequence of words, right? Of course, there is a lot of ambiguity in it. So this is not a trivial task. So as I show you in this example, so if you have 5 characters, 中国外企业, I think a lot of you understand what they mean, right? So if you put it to 中国外企业务, it's segmented into 中国, China, 外企, foreign business, 业务, like business, right? But if you put it into 其中国外企业, okay, that'll be among which, right? Foreign enterprises, right? So the segmentation will be different, okay. So in addition to segmentation, people also study tokenization. So which is to turn a sentence into tokens. So this looks trivial to English, but there is still ambiguity. For example, if you look at period, okay? So if it's after the word Mr., okay, then it's part of an abbreviation, right? But if you put it at the end of the sentence, then it's a standalone punctuation, right? Tokenization will separate out these punctuations and tokens. So one more complicated syntactic task on the word level is part of speech tagging or pause tagging. This task automatically assigns a part of speech to each word. where by part of speech I mean the noun, the verb, the adjective. Most of you have learned them, right? So if I give you the sentence, I can open this can, okay? So the first can is tagged as a modal verb. The last can is tagged as a noun, right? So there is ambiguity. And I can give you a lot of examples where these ambiguities show up. For example, if I give you a sentence, I saw her duck, okay? So if this duck is a noun, right? I saw her duck, I saw her like pet, I saw her toy. But if this saw means see, it means I see the toy. If the saw means to segment using a tool, it means that, okay, I segmented her toy duck or something. Or it can mean I saw her shining away from something, right? I saw her duck, okay. All right, so part of speech tagging is the bottom level of syntactic analysis. And of course, your sentence have a more complicated structure which you can analyze. And to this end, a lot of different grammars can be used. I show you a spectrum of different grammars. There are a lot of them. But I'll use the most frequently studied few to demonstrate what does like syntactic analysis do, okay? So the first of all is called a constituent parsing task. So this task builds upon a sentence a tree structure, okay? In the tree structure, there are a lot of phrases that are embedded in each other. For example, here, Tim bought a book for Mary, right? You can see for Mary is a prepositional phrase, okay? Preposition for, right? So there's a PP on top of it. It means that this phrase is a prepositional phrase, but it's embedded in a verb phrase, bought a book for Mary, all right? The verb phrase is in turn embedded in a sentence structure, the whole sentence. So when you have these like hierarchical phrases, they form a tree, and it's called a constituent grammar. All right. A parser will just take the sentence as input and tell you, okay, what is the tree structure, right? It can help you understand the syntax. But in linguistics, there are other formalisms to denote syntax. And here I show you a second example, which is called a dependency grammar. So rather than like telling you which constituent spans are in the sentence, a dependency grammar will tell you like the word-to-word relations, okay? Like in this example, Tim is the subject, right, for bought. Or is the, like, who bought something. And book is the object for bought, okay, the thing that is bought, all right? And is a determiner, all right? All these word-word relations can be expressed in a dependency structure. So dependency parsing will tell you, okay, in a sentence, what are the word-word relations? All right, these two are the most frequently studied grammars. But you will see more. So in linguistic theory, there are more formal grammars that can express the structure of a sentence. Here, just briefly, there is a grammar called combinatory categorical grammar. Okay, what is this grammar? So this grammar will assign very complicated categories on each word. They look like functions, right? So this bought is a very complicated function, and book is an N, which is a noun, and is an NP, / noun. What does it mean? It means that it will compose with a noun to derive a noun phrase, okay? So what does this bought mean? Okay, it will look for some noun phrase on its right, okay, and compose with it to get something like S / NP. What does it mean? It means it will look for something on its left to get an S structure. So they compose, okay? So what do you think it is looking for on its right? The object, right? What is bought to get this new category. And this new category will look for something on its left. What do you think it is? It's the subject, okay? So a verb is something, this is a transitive verb, is something that looks on the right for an object and then looks on the left for a subject, and composing them will end up with a sentence, okay? All right, this is just to show you another formalism. How do you express the syntax of a sentence? All right. And people have been studying algorithms to implement these parsers, those computational linguists, including myself, right? And sometimes the user does not need a hierarchical tree structure. They only need like part of the tree or spans. So this leads to shallow parsing. For example, you only need to chunk the sentence into noun phrases, verb phrases, etc. So this is a shallow parsing algorithm called chunking. Or people only need to get the categories on each word. So this is called CCG super tagging. All right? The shallow versions of parsing. Okay, so these are roughly syntax. Now let's move on to semantics. All right. There are a lot of things people study in semantics, basically what things mean. And similar to syntax, semantics can be done on the word level or on the passage level. On the word level, okay, so people study word sense. What is sense? So sense is basically the meaning of a word. So if you like open a dictionary, right, you can see a lot of entries. So each entry represents a sense of a word. Okay, so there is a computational linguistics task called word sense disambiguation. So basically, we're given a sentence with a lot of words. We want to know which sense or which dictionary entry each word means. So this is called word sense disambiguation. I gave you two examples. I saw a man who saw a saw. I guess this saw sometimes means see, sometimes means the tool, sometimes means segment, okay? Or sometimes, okay. Or there are other sentences like never trouble trouble till trouble troubles you, etc. So a lot of the same token, right? The same token meaning different senses. All right. Talking about word sense, there are like tasks which are interesting to some of my former colleagues, such as metaphor. Metaphor means, okay, you use something to represent the meaning of something else, right? Or if you say, love is a battlefield, okay, you're using something to denote meaning of some other words, okay? There are also people who study the correlation between a pair of words, okay? When you have a pair of words, they have different relations. And here I list the four of them, like synonym, hyponym, antonym, and meronym. So what do they mean? Synonym and antonym. Synonym means things that mean similar stuff, right? For example, a big and large, okay, they have similar meanings. Okay, antonym is the reverse. I mean, the good, the antonym is bad. Okay, hyponym. Hyponym means the category. Something belongs to a larger category. For example, car belongs to vehicle. Right. So this is a hyponym relation. And meronym is basically a part of relation. For example, the leaf is a part of a tree. Okay. So what do computational linguists do? They develop algorithms that automatically mine out this kind of word-word relations from large data, okay, to gain knowledge about semantics. And if you put a pair of words together, there is also analogy that you can draw, which we will come back to analogy later in week, I forgot which week, okay, when we talk about word embeddings. Anyway, so this analogy is to tell you a pair of words, the correlation between a pair of words is similar to the correlation between another pair of words. For example, king is to queen, okay? It's like a man is to woman, all right? It's like a boy is to girl, all right? So these relations are similar to each other. So this draws analogy. All right. So let's move beyond the word level. Let's look at, on the sentence level, there are also semantic correlations between words. So when you have the sentence, Tim bought a book for $1, for example, so there is a predicate argument structure you can learn. So the predicate is the action, okay? So buy, bought, okay? And to this predicate, there are several arguments, such as the agent or someone who took the action, okay? In this case, it's Tim. And there is another relation, the patient. The patient is like what this action is taken upon, right? And in this case, it's the book. So the predicate argument structure is in the semantics level. And it has correlation with the syntactic correlations as well, right? So if you look at the agent, in this case, it's the subject, right? The patient in this case is the object, right? But semantic correlations are beyond syntax. You can use different syntax to represent similar semantic correlations. For example, the purchase of the book, okay, by Tim costs $1, okay? I can write another sentence to express the same semantic correlations, but this time Tim is no longer the subject, right, of the predicate purchase, right? So semantics are not always correlated with syntax. Okay, so there is a computational linguistics task called semantic role labeling, which automatically identifies these semantic relations between predicates and arguments. All right, but semantic correlations can go beyond predicates and their arguments, or actions and their takers, their patient, agents and patients. We can basically draw the semantic correlation between all concepts in a sentence, concepts and named entities. So this is a graph, semantic graph for the sentence, Tim bought the book for $1. Okay. In the graph, you can see a lot of concepts that are being abstracted. So for example, buy, okay, is an abstract. And there's a person with the name Tim in the meaning, right? And the person is the agent to buy. There's another concept, book. And book is the patient to buy. And the book has a monetary value, right? The monetary value has a unit, dollar, and has a quantity 1, all right? And then when they put together, they modify the concept of book. All right, so this is a semantic graph that represents the meaning of the whole sentence. And when you're given a sentence, you derive the semantic graph. This task is called semantic parsing. All right? And sometimes the semantic representation can be flexible. You don't need to draw a semantic graph. But sometimes you can use other meanings, other ways to denote meaning. So for example, logic, right, can denote meaning as well. In your discrete mathematics, you should have learned first order logic, I think, right? So you can use first order logic to express this. Like Tim bought this book. So I can say Tim X, book Y, and buy XY. All right? So this is a different way to express the meaning of a sentence. So the advantage of using logic to express the meaning is that you can do logical inference. Right? So if I have two sentences, like Tim bought the book, okay? Everyone who bought the book loves it. The second, like this is the second first order logic expression, right? Anyone, if they bought the book, we can infer that they love it, okay? So given these two expressions, then we can infer something that the sentences didn't say, right? We can infer that Tim loves this book by just using formal logical inference. We can get new meanings, okay? So this is what some computational linguists study who are interested in semantics. All right, semantics in the broader sense can also be very practical. Say, if I say, I want to find all the students who scored A+, okay, in the programming course, okay, then I need to look at the database of Westlake University, okay, and select everyone whose score is A+. Or I can say, okay, I want to find everyone who did not pass the linear algebra course, okay. So similarly, I need to look at the Westlake University database. All right, so in this case, I need to turn my sentence, right, into a database query. And SQL is one commonly used database query language, right? So in this case, a semantic parsing task is text to SQL. So basically, we translate the sentence into an SQL programming language sentence. And then I feed this sentence into the database. The database will give me all the entries I need. All right. So that's all we have for semantic parsing. But semantics can go beyond the sentence level. It can also be between two sentences, all right? So one simple example, okay, is paraphrase detection or analogy detection, which is, okay, I'm given one sentence. I want to find another sentence which means the same, all right? So last year we did some research. We found that ChatGPT was really good at finding analogy between sentences. For example, sneezing can be drawn close to volcano eruption. I think this is an impressive analogy that ChatGPT drew to me. But there are other tasks. Here I give you an example, which is called natural language inference. Okay, what is this task? This is a reasoning task. So you're given a premise, okay, and a hypothesis. The task is to tell whether the premise entails the hypothesis or not, okay? So basically it's just to tell whether you can know the hypothesis from information over the premise, okay? For example, if I give you a premise, Tim went to the riverside for dinner, okay? Then maybe I can infer that the riverside is an eating place, right? And I can also infer the fact that Tim had dinner, okay? But I cannot infer the fact that Tim had lunch or Tom had lunch. This is irrelevant, an irrelevant statement. What is more, I know that the hypothesis that Tim did not have dinner contradicts with my premise, okay? So when you're given a premise and a hypothesis, there are three different semantic correlations you can draw. One is entailment, one is neutral or irrelevant, one is contradiction, right? Now let's further move on. This is the last computational linguistics tasks I will show you. This is on the discourse level. As I mentioned to you earlier, right, a discourse is when you put a lot of different subtopics together in a coherent passage. Right? So here I give you a simple discourse. The movie is interesting and Tim wants to watch it. But he did not do it because he has a final exam next Monday. Okay? So this is a discourse. It describes a few subtopics, right? Which I can segment into this picture. Okay? And a computational linguistics task is called discourse parsing. And you can use different structures to express the discourse correlations. And here, this example is called rhetoric structure tree, RST. So what does it say? Okay. It draws the correlation between every elementary subtopic, which I call it a discourse unit, or elementary discourse unit, EDU. Okay. So the first one is the movie is interesting. The second one is Tim wants to watch it. Oh, you know the correlation between the two is a parallel correlation. Okay. And then the third EDU contradicts the first two. Okay, it's interesting. He wants to watch it, but he did not do it this week. He cannot do it this week. It's a contradiction correlation. And then the fourth one further explains all the three, right? Because he has a exam next Monday. All right. All right. So this is a discourse correlation, denoted in an RST. A discourse parser will automatically give you the correlation. As I said, syntactic parsing has shallow versions, right? So for this discourse parsing, you also have shallow versions like discourse segmentation. You're given a big passage. You want to take out elementary discourse units. This is called discourse segmentation. And you can do that based on the meaning of every phrase, every sentence, or based on discourse markers such as and, but, however. Right? Given all this, you can do the discourse segmentation. All right, let's summarize. I showed you through the first type of natural language processing tasks, right? Which is called computational linguistics tasks. These are, okay, on the one hand, very interesting in the cross-disciplinary sense. Linguists and a part of computer scientists, they're interested in those tasks. And I think some of you, okay, I saw that you showed, okay, they're interesting. Some other student in the classroom did not show much interest in them. Okay, so they are one group of NLP tasks. Okay, let me show you a second group of NLP tasks. It's called information extraction. What are these tasks? Okay, so I guess these tasks saw the rise when the internet was built, okay, in the 1990s. So people start to post a lot of things on the internet, such as news, blogs, and other things, okay, products, etc. So all these things are sources of information on the internet, and people start to think, can I monitor the internet and know what people are saying, right? So for example, if you're a company, you want to know what people have been talking about your products, right? Now, which products are liked by people, which products are disliked by people, okay? So if you are a government, maybe you want to know, okay, what's happening all around the world every day, right? So you want to extract the information from the internet, okay? And then the field of information extraction came about under this background. What do people do in IE, right? So similar to like computational linguistics tasks, I can classify information extraction tasks, okay? So, and 4 of the most salient areas under IE are entities, relations, events, and sentiment, okay? And I will show you one after another what they mean. Maybe let's start from entities, okay? So entities are basically what do people talk about out there, okay? So we mostly care about named entities, so which are like things like person names, location names, company names, etc. Okay, and the task is to extract all mentions of named entities from text. Right? I give you an example here. Right? So, so this is a statement. Right? Someone went to somewhere to meet her boyfriend, someone. Okay? So there are 2 persons and 1 location which can be extracted from the sentence. So in political news or daily news, people care about persons, locations, organizations, etc. Right? But for like AI for science, for example, if you have biology literature, right? And people also can extract drug names, like chemical names, like the target names, or some chemical reactions. Those are also under the field of named entity recognition. Okay. But sometimes, and people do not mention the same named entity every time. Okay. Say, Yue Zhang teaches the natural language processing class. Okay. He gave the first class on February the 17th. Okay. Oh, there's a he, right? So you don't say, Yue Zhang teaches the natural language processing class. Yue Zhang gave the first class. Yue Zhang taught. You use different ways to denote the same named entity. So there is a problem you need to resolve, which is called a Navarre resolution. Okay. I give an example here. So Tim bought a book. He liked it. Okay. Here, he refers to Tim. It refers to book, right? Okay, so this phenomenon where the pronoun refers to something before it is called a Navarre. Okay, you want to be able to resolve this ambiguity. And sometimes the Navarre can be omitted. Okay, so for example, this book is interesting. Okay, really like it. Here, you miss the subject I, okay? But you need to automatically find, okay, there is a 0 pronoun or a missing pronoun, and then identify it. So this is called 0 pronoun resolution, okay? Maybe in languages such as Chinese, this is more frequent. But sometimes you see a sequence of sentences without subjects, right? And you can know what each sentence means, okay? All right, so a correlated task is called coreference. coreference resolution. So basically, you're given a chunk of text, okay? You want to extract all mentions of the same entities and put them together, okay? So I give you one example, right? So Tim watched 8 Harry Potter movies. He found the series fascinating, okay? So here there are 2 entities, right? So one is Tim the person, one is like Harry Potter movies, okay? And each entity was denoted with 2 different mentions, okay? We extract them out, put them together, and refer the entity to them, okay? Coreference resolution. All right, this is so much to say about entities. As I mentioned earlier, right, information extraction covers entities, relations, events, and sentiment. So the second thing is relations. Now, the relations between entities, they form knowledge. Okay? For example, if I say Trump is the president of the United States, I tell you a relation between 2 entities, right? So someone who takes some role in a country, right? So similarly, I can say Mary is the girlfriend for Jason, all right? So this is a personal relation. So when we talk about knowledge, we show a lot of different relations. And here, for example, I listed a few, right? Bangkok is a city in Thailand, okay? Pad Thai is a food of Bangkok, right? So all different kinds of relations. So Hilton is a type of hotel, right? Bill Gates was one of the founders for the Microsoft company, etc. So this form knowledge. How do you get this knowledge? You can get this knowledge by reading a lot of texts, right? So one task called relation extraction will identify all these relations between named entities, right, from free text. So here, I give you one sentence, right? So in this sentence, there is a personal relation, right? There is an organization affiliation relation, right? And there is a physical location relation. Okay. So basically, Tim and Mary, okay, they have a social relation. Tim and Microsoft Research Asia, MSRA, has an organization affiliation correlation. And MSRA is located in Beijing. So this is a like geolocation relation. So what do you do after you extract all these relations? You can put them together and they form a graph. So in this graph, okay, the nodes are the entities you have. The edges are the relations you extract between the entities, right? So this graph is called a knowledge graph, okay? And you can use a knowledge graph to store the information you extract from free text. Since we mentioned knowledge graph, let's look at 2 tasks related to it. So the first task is called entity linking or entity disambiguation. Why do we have this task? It's because when we have one entity, there can be different ways to mention it, right? So when you recognize all these mentions, you want to know, okay, they mean this node in my knowledge graph. Okay, so this is something that is non-trivial. Or one entity can also be ambiguous. It can relate to a lot of, one mention, okay, can be ambiguous, relating to a lot of things. For example, when I mention Apple, okay, I might mean a company named Apple, or I might mean a kind of fruit, okay? So which entity in my knowledge graph should I link this apple to? It takes some computation to resolve this ambiguity. So this is called entity linking. Or we can normalize the named entity into a canonical mention. So this is called named entity normalization. All right, this is the first task related to knowledge graph. There's a second one, okay? No knowledge graph is complete. No matter how many edges you can build between nodes in the knowledge graph, there can always be missing edges, okay? I give you an example. If I say John is a singer, and then I say John is from Rome, then we can infer, okay, a lot of things from it. So because we know Rome is in Italy, right? So when I know John the singer, John is from Rome, I can infer that Italy has a singer. All right? So when you read a lot of documents, these documents cannot express all these trivial links between entities. So inference is important for knowledge graphs. Okay. When you have some existing edges, you want to infer new knowledge. This is called inference, link prediction, or knowledge graph completion. All right. Now I've mentioned entities and relations. The third item in information extraction is events, okay? I have a trader friend who says everything about the world is events, okay? And to some extent, it's true, right? It's events happening all around us. So event detection is to automatically extract what happens in a structure from text, okay? So, for example, if a news says Trump visited Tokyo, okay, then we can extract one event of the time diplomatic visit. And there's a visitor, there's a location, etc. Okay? So according to news, we can extract a lot of different events. There are other ways we can extract events. There is a task called first story detection or news event detection. So this is the extraction of an event from social media, from sources which are even earlier than news agencies, okay? We don't need to wait when news reporters write about an event to know that some event happened. For example, I remember there was an earthquake last year, okay, where we can feel it in Hangzhou. So I remember I was driving on the road, and I stopped to wait in a red light, and I felt that my car was shaking, and I thought some heavy vehicles must have passed by or something. But it turned out that it was an earthquake. It happened at, I think, 8 a.m., if you remember. And when that happened, a lot of people, they write in their social media. They say, oh, I feel something is shaking when I sat on the sofa. Or someone posted, okay, my mug fell to the ground or something. So when you see these clues, right, over social media, you can guess something's happening, especially if you monitor social media in one area. You can collect this information and you can detect a first story, okay? And why is it important? Because natural disasters, such as earthquakes, they happen very fast, okay? If the rescue people know, okay, firsthand that something's happening, they can quickly prepare, right, to do something to help people. So first story detection is important. And there are other things we care about events. For example, factuality prediction. So when people mention events in different ways, people indicate different chances for the event to happen. For example, if some event has already happened, then that was a sure event. Okay? But if someone says, I will do something, okay, of course, depending on the person who makes the statement, you can guess. This is likely, a likely event, right? If someone says, okay, I guess something will happen, then this is a less likely event, etc. So we can guess the likelihood of events, factuality of events. One more thing is timeline extraction. So in a piece of news or in a history text, in your history book, you can see that, okay, there are a lot of mentions of events here and there, and there are clues that some events happened before some others, okay? And you want to find the chronological order between the events so that you can draw a life story of someone, for example. And this needs the resolution of event temporal order to find, okay, in which time span does an event happen, okay? So the last thing people cared about is the causality. And sometimes they mention, okay, this event caused another event, okay? Implicitly or explicitly. For example, if drunk driving caused a crash, okay, then it is useful, right, for the lawyers to know, okay, who is responsible for something, okay. When we mention events, we can also use pronouns or zero pronouns, okay. I give you an example here, where the sentence says, I interviewed Mary yesterday. It went smooth, okay. So this "it" refers to the interview event, okay. So this is the event coreference. It can also be zero pronoun. So, for example, if the sentence says, Mary went to Russia to see the World Cup, and Tom too. Okay, there's no mention of the verb. This is called verbal ellipsis. Okay, but you can also infer that another event happened. So Tom saw the World Cup as well. All right. So lastly, when you have a lot of events which have their own logical correlations, and these events form a larger theme, a larger event, and this is called a script. Okay, it's under the semantic frame domain. Let me give you an example. So if you visit a restaurant, okay, it's a script. What do? You need to enter the restaurant, and you need to be seated, right? You need to look at the menu. You need to determine what to eat. You need to order the food, and then the food must be served, and then you eat the food and you pay the bill, right? And then you leave the restaurant. There are a lot of sub-events within this big event, and it's a script. You could automatically learn knowledge about a script from free text, which helps you to understand some unknown events or some known events. Okay, this is called script learning. Okay, the last thing people care about in information extraction, it's sentiment. Sentiment, of course, tells you the attitude of someone towards something. All right? So there are different ways you can formulate a sentiment task. And here I give you 4. Okay, the first one is very simple, sentiment classification. So it basically tells you whether a sentence is positive or negative. Okay, so I say, I like this movie. Okay, positive sentiment. Okay, this movie is boring. Negative sentiment. So it's a sentence level classification task. Or if I tell you the sentence, I saw a movie, then this is a neutral, right? Doesn't bear sentiment polarity. You can do it like in a more fine-grained way. For example, I say iOS is better than Android. If you make such a statement, then you have a comparison, right? Where you have a positive sentiment towards something and a negative sentiment towards another thing. This is called targeted sentiment. So you mention different targets in a passage and you have a sentiment on each target. This is called targeted sentiment analysis. If you talk about a product, a lot of sentiment analysis are needed in product reviews because, as I mentioned, companies care about these, right? So if it's a product review, you can have different aspects about a product. And this is called aspect-oriented, aspect-based sentiment analysis. So you have a maybe computer, laptop computer, all right? The CPU is one aspect, right? The design, how it looks like, is another aspect, right? The weight, is it light, okay? The size, different aspect. And the user might comment on different aspects about the same thing. And aspect-based sentiment analysis will extract, okay, all these aspects and then have a sentiment polarity on each one. The last one is more theoretical, okay? So if I say someone blamed someone else for something, you know, there's a sentiment like opinion holder, right? Someone. There's an opinion target, okay? Someone who's blamed, right? There's a reason, the rationale, why this negative sentiment happened. So people try to extract all these fine-grained sources of information in order to analyze the sentiment. Okay, this is sentiment. Okay, there are also people studying different tasks related to sentiment analysis. One thing is sentiment lexicon acquisition. What is it? So the sentiment of a text is represented by sentiment-bearing words, I should say. For example, like bears a positive sentiment, okay? Boring is negative, okay? Intriguing is positive. So sentiment lexicon acquisition uses an algorithm to extract automatically from text all these sentiment-bearing words. Okay, this is a related task. Or emotion. Emotion is it's related to sentiment, but it's sort of more fine-grained in the sense that anger, disappointment, etc. are all a negative sentiment, but there are different emotions. Okay, there's also sarcasm detection. Okay. If I burn something when I cook and I say great, so I didn't mean that this is great, but I've been sarcastic. Okay. Sarcasm detection is to automatically find, okay, whether people are sarcastic when I say something. Okay. Oh, the football team is really great. Okay, it can be actually a negative comment. It depends on the context. There's also a task called stance. Okay, stance means, okay, I support something or I do not support something. This is related to sentiment, but it's not quite, okay? So it's more like an attitude without emotion, right? For example, I support plastic bags, or I do not support the use of plastic bags, okay? And when you have a stance, when you have a claim, it's normally supported by some premises, by some arguments, okay? I do not support the use of plastic bags because they pollute the environment, okay? So because, the thing after because, okay, is an argument to support my stance, to support my claim. So argumentation mining automatically analyzes text and tells you how the author writes the text to support the claim. Okay, so this is another task. All right, so that's all for information extraction. So basically, we have looked at computational linguistics, and we have looked at information extraction. Okay. So one last comment about information extraction is it's sort of quite useful for automatically mining knowledge from the literature, right? So for those of you who are doing AI for science, it's very related too. So the third big category of natural language processing, and also the category which is more relevant to today's research in LLMs, is generation. Okay, natural language generation, by the name, you mean it's how to use algorithm to generate some text. So I start with a very theoretical one called realization. So this is related to computational linguistics. So the input is a semantic graph, okay? And the output is the corresponding sentence, a sentence that bears the same meaning as the graph. So basically, surface realization is how do you spell out the semantic meaning, which is represented by a graph structure in text. Okay, so this is the reverse of semantic parsing. Right? Of course, you can use different text to represent the same meaning. And if the input is different, the output is also text. There's a task called data to text. So, for example, you can have a database. The database can be some statistics about a basketball game. Or the database can be some statistics about the stock market for one day. Okay? And it translates this into narration, into text, to describe, oh, the stock market rose in the morning, okay, and then fell in the afternoon, okay, from which point to which point. So this translates, okay, the structured table into text. It's called data-to-text generation. Is there text-to-text generation? There are a few examples. One is called text summarization. So when you read Baidu News or Google News, you will see this is a piece of news and there's a small paragraph describing the news. This already uses summarization technique. Okay, so the algorithm will read a lot of news, okay, and then summarize them together into a small paragraph describing what happens, and then give you the link about these news. Or you can also summarize one or multiple pieces of text into a title. This is called title generation. Or even smaller, into a few key phrases to describe what happens. Okay, key phrase generation. So if the input is one language and the output is another language, so this is a very traditional computational linguistics task called machine translation. Okay, is nowadays quite reliable in some domains, such as news, but still not so reliable for some languages and for some domains. There's one more task, okay, text to text, which is called grammar error correction. The basic idea is you're given something written by some second language users, for example, or when you try to write something quickly, okay? And then you pass that to a system, okay, to turn sentences with grammar errors into sentences that are fluent and correct. So this is called grammar error correction. Or you can use AI to polish your written work, okay? So polishing. As in my class, you're very encouraged to use AI to polish your work, okay? So whatever you write. Okay, one last text generation task is QA. So there are different ways to answer questions. So one is to answer a question according to a knowledge graph. You have a big knowledge base, which you extracted from free text, okay, containing knowledge from the internet. And then someone asks you a question, such as, what was the first Taylor Swift album? Okay. Then you need to do some inference from your knowledge graph to find the answer. Maybe in the beginning, you need to find all the albums by Taylor Swift, right? And then you need to order them by the publication date, okay? In the end, you find the minimum date for the album, which was the first one by the artist. This is called knowledge-based question answering. You can also answer questions by reading paragraphs. And one task is called reading comprehension. So the algorithm is given a passage, okay, and then given a question. So for example, the passage can talk about rainfall, what caused the rainfall. And then the question can simply ask, okay, what causes, okay, the raindrops to form? You can directly find the answer from the passage and then to give the user. So this is called machine reading comprehension. Or say, if you are an internet website such as Zhihu or Yahoo Answers, there are a lot of questions that people frequently ask, which forms a community. Then you can use an algorithm, right? When you have a question, you use the algorithm to match the question to some of the questions people already asked, okay? And you find, okay, someone has already asked a similar question and people have answered it, so I don't need the algorithm to answer it. It needs only to retrieve, okay, the relevant answer. So this is called community question answering. Okay, the last one, and maybe the most challenging one, is open QA in the open domain. So you don't tell the algorithm anything. You just ask the algorithm one question. The algorithm is supposed to give you the answer. And this is what most large language model does, right? So if you ask DeepSeek, okay, so where was the first Olympic Games held? Okay, DeepSeek will directly tell you an answer. There are two ways it tells you the answer. So the first is that, okay, the model itself has the knowledge. It just directly generates the answer to you. The second is the algorithm looks into the internet, okay, retrieves some relevant documents, and then performs machine reading comprehension. Right? For example, it can retrieve a Wikipedia page, okay? Okay. Sometimes if you use models such as DeepSeek, I think it shows you, right? I'm retrieving 14 documents, right? I found 14 related documents. And then it reads the document, performs machine reading comprehension, and tells you the answer, okay? So this is OpenQA. But the interaction can go beyond one round of interaction, okay? For example, there can be chat, okay? Either chit chat or task-oriented chat, okay? If you're not satisfied with your first answer, you can further ask questions. The model will further interact with you, okay, to refine the answer or give you more information. This often happens to writing, okay? Here I gave you an example. You ask ChatGPT, write me an email about something, okay? Help me write an email to say hello to my neighbor, okay? And then ChatGPT can write you an email, and you might find, oh, this is too formal, okay? I want a more casual tone. So you tell ChatGPT to turn it into a more casual email or to add some content. With a lot of rounds of interactions, they can do that. And as most of you know, these large language models can do more than just writing an email. They can also write code, okay, and give you brainstorming, give you ideas about something. So they are more and more helpful in a sense. Okay, so I took you through 3 topics: computational linguistics, information extraction, and text generation. So there are a lot of related fields also where natural language processing technologies have been used. So I tell you a few. Maybe you have separate classes for them, okay? I'm sure you will have a class called information retrieval. So this is to retrieve data from the internet, from a large corpus, etc. The search engines, such as Baidu, they do information retrieval, okay? And your large language models, if you use retrieve augmented generation techniques, they also do retrieval. So why are natural language processing techniques useful? So sometimes in IE, people need to classify the categories of documents. So document classification is traditionally studied in IR, information retrieval. Or spam, like when you have a lot of emails, you try to predict whether those emails are useful emails or like phishing emails, spam emails. So this belongs to the category, but uses natural language understanding techniques to help you. Right? There are also language identification. You want to know this website is written in French or in Japanese or in English. Okay, language identification, etc. These are in information retrieval. And another related field is recommendation systems. So basically, the systems, they recommend things to users. For example, you can recommend a product to the user, recommend a piece of music, or recommend a video clip. We all know TikTok, right? So it's a recommendation system. Or the Red Book, okay? So it's a recommendation system. So they can recommend things you like to watch, okay? So why is it related to natural language processing? Because when recommending a product, you need a thorough understanding of the product description and customer comments, etc. So this uses natural language processing techniques, right? When I say bioinformatics, this is really a big field, okay? So basically, they use AI technology to help biology study. AlphaFold, a very famous tool, right, to analyze the protein structure, belongs to the field of bioinformatics. But bioliterature review, which uses AI technology to understand a lot of papers also belongs to bioinformatics, which uses natural language processing techniques, right? So even things like AlphaFold, they use technologies related to NLP, which you will learn in my course, okay? Text mining and text analytics. So this belongs to business analytics. So you want to find useful information by inference over large text. So, for example, the medical doctor automation. So this needs text mining to read a lot of medical documents. Stock market prediction needs the reading of a lot of news and company reports. Okay, and there has been movie revenue prediction, right? People reading customer reviews, reading descriptions about the movie, reading news to predict, okay, the ticket house income of a movie.哪吒 2, people have been predicting the revenue of this movie, right? Okay, people have been predicting the result of presidential elections as well. All right, so the last related field is AGI and ASI. What are they? AGI is artificial general intelligence. Okay, ASI is artificial superintelligence. So basically, if I draw the capabilities of AI in one circle, right, and I draw the capabilities of humans in another circle, they have overlaps, right? There are a range of things AI can do and humans can also do. But there are things AI can do but humans cannot do, right? Multiplying 10-digit numbers, okay? Getting knowledge all over the world, okay? And these things AI can do much better than humans. But there are things human can do but AI cannot do. Reasoning, okay? Performing reliable decisions in unseen scenarios. In unseen scenarios. For example, I've learned how to drive. And I can drive in roads and off-road. But FSD cannot do it very well because it's not so reliable in unseen scenarios. Okay? And GPT-4, it makes hallucinations. By hallucination, I mean sometimes it tells you things that are not true. Right? Sometimes I ask GPT-4, okay, can you help me find a paper? It gives me a paper title, it gives me all the authors, it gives me the affiliations and the abstract. And it turns out that none of them were real. Okay? So this is called hallucination. Okay, I'm talking about AGI, which is where people try to make AI do what it cannot do, but humans can do right now. Okay, and if it surpasses human intelligence, then it's ASI. Okay, and this involves multimodality reasoning. So this involves things beyond natural languages. Okay, for example, there are algorithms such as Sora, which can help you generate a small video clip according to a description. Okay, there are also figure, and this Yu Shu, etc. So who builds these robots, okay, and driven by large language models that can interact with the physical world. All right. So this is called embodied AI. So that's all. Okay. If someone asks you what is NLP about, then you can say, okay, in the broadest sense, it's anything related to automated processing of text. Okay. So it includes computational linguistics, information extraction, natural language generation, and a lot of related fields in AI. That's natural language processing. okay, how am I going to teach you so many things? Okay, we only have 16 weeks. Okay, I'm not going to teach you through one task after another, because not all of you are interested in all these tasks, and some of you are only interested in a small number of tasks. Okay, I'm going to teach you natural language processing based on machine learning, based on the nature of machine learning tasks that they belong to. Okay, why should we learn natural language processing from a machine learning perspective? No, we have to review some history, and you will know why. First of all, I briefly tell you how the field evolves, okay? Natural language processing started in the 1950s when computer science and AI dawned, okay? And people, they talk about what is artificial intelligence, and they realize natural language processing is a key component in it, okay? You need to understand natural languages. But at that time, people tried to hire a lot of linguists. They write rules to process languages, okay? So if the previous word is an adjective, then the next word is likely a noun. It's a noun. If then. You all learned programming. You can think about a program that consists of 10,000 lines of if, and then this if else, if, and then if else, okay? This kind of things, okay? They coined a lot of linguistic rules to handle this phenomenon. And that was the early technology for natural language processing. But then suddenly one day, people realized it's not going to work, because languages are so ambiguous, and no set of if and else statement can cover these flexibilities, okay? Okay, there is a more famous example than the duck one I gave you. So the example was a report to funding agencies, okay? And in which people found when you translate the spirit is strong, but the flesh is weak into Russian. Why Russian? Because in the 1950s, the US and Soviet Union are in Cold War, okay? And people try to understand each other automatically, okay? And when people try to translate this one, the result is the vodka is good, but the meat tastes badly, okay? So which is completely not the same as, okay, what people try to say. Why does this happen? It's because flesh is ambiguous. Okay, spirit is also ambiguous, right? It can mean whiskey, vodka, and things in line, multi, okay. Right, so no linguistic rules can handle all these ambiguities. And then the funding agency was not happy. And then natural language processing funding was cut. And a lot of professors, they start to find jobs elsewhere. Or they start to work on other places, okay, other topics. But then, at the end of 1980s, things changed a bit. People build computer hardware that are faster. The IBM servers, right? They start to build servers that are fast, that can do a lot of computation. And at that time, people start to think, oh, can I build a statistical model to handle ambiguities? All right. So rather than having a linguist, right, writing a lot of rules, if then, then I can ask the linguist to annotate a big corpus. By corpus, I mean a big set of data. Okay, we will learn about them next week. Okay, they annotate the linguistic structures on those data. And then I build a machine learning algorithm, okay, to learn from this data. And then according to statistical knowledge, I know that given this sentence, the spirit is strong, but the flesh is weak, okay, we know it's more likely to mean this rather than that, the probabilities, okay? And you know, the IBM, they start to build probabilistic statistical machine translation systems and machine learning driven speech recognition systems. And they work. They're more accurate than linguistic rules, or at least competitive to them. And people start to think about how to build machine learning models from them. And people have get a lot of new fundings, all right? And the field start to boom again. So it all went very well until the mid-2000s, actually 2010s, when neural networks start to become the dominant approach in the field. Why? It was because the early method, which you will see through my course, okay? They are statistical, they're mathematically elegant, but they are less powerful than a neural network with many, many parameters, okay? When the computation power increase, people start to use neural networks which are less mathematically elegant, okay, less interpretable, but more powerful to solve these problems, okay? You know, and then recent years, people start to further increase the size of training data and size of the neural networks, and then they build large language models. This was from maybe 2018 to now, okay? A lot of names from Sesame Street came out. And BERT was one famous model, and then GPT came out, and then at the end of 2022, ChatGPT caused a lot of interest to happen. And nowadays, large language models are still evolving, and we're in this stage. So if you look at the keywords, okay, from the AI research field, you will find that these keywords, they change over time, okay? In the 1950s, people care about grammar, about knowledge, speech, word order, etc., these things, database, linguistic. And then after the 1990s, then people start to think about some other tasks, okay? And machine learning features became dominant. And then from 2015, you can see deep learning and transformer start to become more and more frequent. Now this means that the field is dynamically changing. And as a result, okay, the tasks have received different attentions. Some old tasks, they die in the research literature. Some new tasks came out, okay? Maybe from the very early ages, people cannot do full tree parsing. People do some like prepositional phrase attachment problem. Okay, what does it mean? When I say I eat pizza with fork, and when I say I eat pizza with cherry, okay, the prepositional phrases with something, they modify different things. When I say I eat pizza with fork, it modifies eat. When I say I eat pizza with cherry, it modifies cherry. So in early days, right, people cannot do full sentence parsing. They do this kind of ambiguity resolution. But later, when full parsing was already accurate, so this problem dies out. Okay, I'll give you a second example. So before large language models came out, people devised all different ways to do text summarization. Okay, so we also built a model, you know, called Gemini. So in the same year as Google released their large language model Gemini. So, and after large language models came out, no one works on text summarization anymore because those can be handled by large language models. Okay, so research on text summarization gradually died out. So in this sense, it doesn't, this is not so effective if I teach you one task after another. So maybe after my class, you will realize, oh, this task already died, okay? So, but the technology behind different tasks, they remain relatively stable. Here I just give you an example, right? So no matter what kind of tasks they are, they can be categorized into classification, where the output is one class label in a set, okay? Positive or negative, okay? Spam or not spam, etc. Entailed or not entailed, contradict, etc. So this is called classification. Structured prediction, where the output is a tree or a sequence or some structures, right, with substructures. No matter whether it's relation extraction or semantic parsing, they are all structured prediction tasks, okay? Or generation, the output is a sequence of text. No matter it's coding, email writing, or question answering, or machine translation, it's a generation task. So the nature of the tasks, the machine learning of the tasks, they are relatively stable, right? So we should learn the underlying technology, especially those machine learning technology that are developed for natural language processing. So in summary, I gave you a review of NLP. I showed you basically the whole spectrum of NLP problems people study. And I briefly explained to you why should we learn NLP from a machine learning perspective. And here is an outline of this term, which you will find very useful in deciding whether you want to learn this course or not. Okay? I will give you a very detailed explanation of the picture next week. But roughly, you will see. Next week, we'll give you an overview, okay, of the framework of using machine learning to solve NLP problems. This framework is very common for all the other weeks we learn, okay? Then, from week 3 onwards, okay, you will start to learn one technology after another, okay? So these weeks are basically organized in the chronological order of the development of the field. For example, week 3 will be some techniques used in the 1980s and 1990s. Then you will say, okay, if the technologies are used in the 1980s, why should we learn them? Okay? So weeks 3, 4, 5, 6, 7, you see I boxed them together. They are called linear models, okay? And they can be I summarize them into one neuron. Nowadays, everything is a neural network, but these linear models are one neuron. And a lot of the concepts they use, okay, they are the basis of learning neural networks, so you still want to learn them, okay? And I don't introduce them as I introduce in the machine learning class, but I review them in the background of natural language processing. So we're still introducing natural language processing, okay? And then you will see that we spend a lot of weeks talking about neural network models, okay? And they are very correlated. I'll tell you the details. But these weeks, or the majority of the semester, we will build different neural networks to solve different natural language processing tasks, okay? And then in the last 2 weeks, we will learn large language models, okay? How to train large language models, what they are, and then how to use them, implications of them, okay? So that's the semester structure.